What specific problem does the SelfCite framework aim to address in the context of citation generation, and why is this issue particularly important for language models?
The SelfCite framework addresses the problem of generating accurate and contextually grounded citations in responses produced by language models. This issue is crucial because citations must not only support the generated statements, but also be relevant and precise, ensuring that users can trust the information provided. SelfCite introduces a self-supervised reward mechanism based on context ablation, which evaluates citation quality by measuring necessity and sufficiency scores. By optimizing citation generation through methods like best-of-n sampling and preference optimization, SelfCite enhances the model's ability to produce citations that are both necessary for the statements and sufficient to support them. This improvement is vital for maintaining the integrity and reliability of information in language model outputs, especially in applications requiring high accuracy, such as academic writing and information retrieval.
How does the SelfCite method work? Please illustrate its algorithm step by step, including the roles of the necessity score and sufficiency score in the evaluation of citation quality.
The SelfCite method operates through a structured algorithm that enhances citation quality in generated responses. First, it generates a response using an autoregressive language model, LM, based on a given context and query. Each statement in the response is followed by a citation sequence referencing relevant context sentences. The quality of these citations is evaluated using two key metrics: the necessity score, which measures the probability drop when cited sentences are removed from the context, and the sufficiency score, which assesses the probability hold when only the cited sentences are retained. The final reward combines these two scores, ensuring that citations are both necessary and sufficient for supporting the response. The algorithm then employs a best-of-n sampling strategy to select the optimal citation set that maximizes this combined reward, refining the citations while keeping the response statements unchanged.
Can you explain how best-of-n sampling and preference optimization are integrated within the SelfCite framework? Provide a detailed description of their roles and how they contribute to improving citation quality.
In the SelfCite framework, best-of-n sampling and preference optimization work together to enhance citation quality through a systematic approach. Best-of-n sampling generates multiple candidate citation sequences for each response statement, allowing the model to select the citation set that maximizes a combined reward metric derived from necessity and sufficiency scores, which evaluate how well the citations support the generated statements. This process is crucial as it ensures that the citations are both necessary and sufficient, thereby improving the overall citation quality. Following this, preference optimization (SIMPO) internalizes the gains achieved through best-of-n sampling by training the model to generate better citations directly, without needing to sample candidates each time. This is accomplished by using preference data pairs, where the model learns to distinguish between original outputs and those improved by best-of-n sampling, thus refining its citation generation capabilities. Together, these methods enable the model to self-improve its citation quality by leveraging self-supervised rewards from context ablation, ultimately leading to more accurate and contextually grounded citations.
What empirical results were achieved through the implementation of SelfCite, particularly in terms of citation recall and precision? How do these results compare to existing methods?
The implementation of SelfCite achieved significant improvements in citation quality, with best-of-n sampling, BON, increasing the overall F1 score from 73.8 to 77.5 and further applying SIMPO raised it to 79.1, the highest across the datasets. These results indicate a consistent enhancement in both citation recall and precision across various tasks. In comparison to existing methods, SelfCite outperformed LONGCITE 8B9B models and surpassed proprietary model prompting while producing shorter citations. Notably, SelfCite's approach was more effective than ContextCite, which relies on context ablation for estimating sentence importance, as SelfCite re-ranks existing LLM-generated citation candidates, leading to more efficient and accurate citation quality estimation. Overall, SelfCite demonstrates a clear advantage in citation quality without the need for human annotations or extensive computational resources.
What are some limitations of the SelfCite framework in terms of its approach to citation generation? How might these limitations impact its applicability in real-world scenarios?
The SelfCite framework has several limitations regarding its citation generation approach. Firstly, while it employs self-supervised rewards based on context ablation, this method may not fully capture the nuances of citation relevance, potentially leading to citations that are necessary but not sufficient, or vice versa, as indicated by the necessity and sufficiency scores. Secondly, the framework relies on the autoregressive language model's ability to generate accurate citations, which may be hindered by the model's inherent biases or limitations in understanding context, as seen in the qualitative examples where incorrect citations were generated. Additionally, the preference optimization process, while effective, requires substantial memory and computational resources, which could limit its scalability in real-world applications where resources are constrained. Lastly, the iterative preference optimization may not completely eliminate the risk of reward exploitation, which could lead to overfitting on specific citation patterns rather than fostering genuine citation quality improvement. These limitations could impact the framework's reliability and effectiveness in diverse real-world scenarios, where citation accuracy and contextual relevance are critical.
What future work or improvements do the authors suggest could address the current limitations of SelfCite or enhance its functionality further?
The authors suggest several avenues for future work to enhance the functionality of SelfCite. One key improvement is the exploration of on-policy methods like proximal policy optimization, PPO, to further enhance performance, as they believe that such methods could better maintain consistency between the generated data and the model's evolving output distribution. Additionally, they mention the potential for iterative preference optimization, which has shown to yield improvements over multiple rounds of training, indicating that further iterations could refine citation quality even more. The authors also express interest in developing better data mixture strategies during the supervised fine-tuning SFT stage to improve answer correctness, as they noted a slight degradation in correctness when using context-site SFT data. Lastly, they highlight the need for more efficient methods for contributive context attribution that do not rely on extensive context ablations or computationally expensive techniques, aiming to streamline the process of citation generation.